Okay, on page 1 we looked at 5 functions and 5 rules. Those involve derivatives and antiderivatives. Now let's look at 5 theorems. Before we jump into this, I just want to make one note about make a comment here about some notation. I'm going to be referring to both open and closed intervals on this page. So please make sure you remember that this indicates an open interval. Open intervals do not include the endpoints. And closed interval. And a closed interval does include the endpoints. So the way I'm going to present these theorems, I'm first going to look at the conditions that are required in order for you to use these theorems. And this, anytime you use a theorem, with the exception of FTC, that's the only one where I don't think it's necessary for you to state that the conditions exist. But anytime you use one of these other 4 theorems I list here, you must state that the conditions required are in place before you use any conclusions from that theorem. Okay, so let's jump into this first one. Differentiability implies continuity. This one requires that the function in question is differentiable on an open interval from a to b. And what are the consequences of that? This theorem tells us that if it's differentiable on that interval, then f of x is continuous on that interval. And this one is, we often talk about this theorem and we say, oh, well, let's think about the converse. Does continuity imply differentiability? And the answer to that is no. So it might be worth noting that here. The converse of this is not always true. If you want to see counterexamples, see y equals absolute value of x, or y equals x to the 2/3 power. You're going to see the corner and cusp example there where the function's continuous but not differentiable. Okay, let's move on and let's now talk about the extreme value theorem. Conditions required. Now f of x has to be continuous, and this time it's closed interval. If f of x is continuous on a closed interval, then f of x has both a min and a max on the closed interval from a to b. Okay, a couple comments here. When I say min and max, I'm referring to absolute, not local, or not relative. And the e in extreme value means that the function takes on extreme values. It has both a min and a max, even if it's a constant function. If it's a constant function, think horizontal line, then the min and max are the same. I do want to jump back real quick up to differentiability implies continuity. One thing I forgot to mention up here, I will be going into some other mini lessons talking about continuity and limits and how those two things work together. So those things you're going to want to make sure you pay attention to those things too, because sometimes that crosses over into this differentiability implies continuity theorem. Okay, let's now move on and talk about IVT. So for IVT, and the I stands for intermediate, for the intermediate value theorem, the conditions required are this. That's the exact same condition we had for the extreme value theorem. Now, what does the intermediate value theorem tell us? It tells us that f of x takes all values from f of a to f of b. So if we have a function, let's just do a quick little graph here. If we have a function and it is continuous on a closed interval from a to b, then that function takes all values from f of a to f of b. So when might you need to use this theorem? Oftentimes, this theorem will come up in a question where you're asked, hey, does this function, does this particle, does this tank ever reach a quantity of, let's just pick a number, like we'll just say 5. And if you can first prove that that function is continuous on some closed interval and 5 falls between f of a and f of b, then you can say, hey, by the intermediate value theorem, I know the function takes that value at some point on the interval. By the way, this is called an existence theorem. It tells us that it does take all of the values from f of a to f of b, but it doesn't tell us where a specific value exists on that interval. All right, let's move down to the next theorem, the mean value theorem, MVT, and this is more appropriately known as the mean value theorem for derivatives, because there is also one for integrals. So, mean value theorem. This one requires two conditions. They are, so the function has to be continuous on the closed interval from a to b, and f of x has to be differentiable on the open interval from a to b. So those are the conditions required, and here's what this theorem tells us. There exists, another existence theorem, a value x equals c such that, so this theorem says that f prime of c, there exists some value x equals c on the interval, such that f prime of c equals f of b minus f of a, all divided by b minus a. And you might remember this as the instantaneous rate of change at some point on the interval is equal to the average rate of change across the entire interval. All right, so that's MVT. Let's now move on to the granddaddy of all calculus theorems, and that is FTC. FTC is so important, it has two parts. For part one, only one thing's required. The function f of x is continuous. That took me a second there. That's not how you spell continuous, folks. You deserve better than that. There you go. Continuous on the closed interval from a to b. And what is FTC part one? Well, it's how we evaluate a definite integral. So if we want to evaluate the definite integral from a to b of little f of x dx, we simply find the antiderivative big F, we plug in b, we plug in a, and we subtract that quantity. Remember, a definite integral is a number. An antiderivative is a function. Another familiar form of this you might see is this one. And that says that and I'm going to write this out for you so you can see it, some final amount equals an initial amount plus the integral of a rate. Another way to think about this, and I'm going to show it in slightly different notation for you here, I could also say that little f of b equals little f of a plus the definite integral from a to b of little f prime of x dx. Okay, so just showing you a couple different forms there for FTC part one. FTC part two is got the following condition. The function f is continuous on an interval, and I'll just call that interval I, big capital I, often used in calculus textbooks to indicate some unknown interval. That interval contains the number a, and the following is true for all values of x on the interval I. The derivative with respect to x of the definite integral from a to g of x of f of t dt is equal to f of g of x times g prime of x. And I want to just provide a couple notes of commentary here. So this is what I like to call the derivative of an accumulation function. And if you recall from class, we kind of used some general student-friendly language here, and we said you take the upper limit of integration, you plug it in for t, you can see that right here, and then you multiply by the derivative of the upper limit. So that is Fundamental Theorems Calculus Part 2. Okay, so let's just kind of zoom out here and summarize all this stuff. For the theorems that I mentioned here, for differentiability implies continuity, extreme value theorem, intermediate value theorem, and mean value theorem, it's very important for you to state those conditions before you state the consequence of the theorem. And a lot of those conditions sound similar. Sometimes the intervals are open, sometimes the intervals are closed. Make sure you know which times the intervals should be open and which times they should be closed. Typically, we talk about continuity on closed intervals and differentiability on open intervals. And the reason why is because we can't differentiate a function at endpoints. That's why we always talk about differentiability on open intervals. For FTC, down here, there's no need to state those conditions. If you need to evaluate a definite integral, you do it with FTC part 1. Don't need to state the conditions. If you need to take the derivative of an accumulation function, you do it with FTC part 2. You don't need to state the conditions. But that's the only case where you're applying a theorem without stating the conditions first. All right, folks, that's it for today.